Good evening. This is Professor Shina with the MECH.5710 Quality Engineering course. Tonight we're going to talk about the use of Minitab to solve some of the problems that we worked on during the semester. In particular, solving the problems of week 3, that is using GR&R, and week 5, which is the control charts. So I'm going to try to show you how to solve these problems with Minitab. We've already solved them before using mathematical methods and formulas. Now we're going to solve them using the software, which would make it much easier. So to start with the GR&R on week 3, we have a methodology of understanding the error due to equipment and operator variation. This is very important in terms of especially the supply chain. We have most companies depending on suppliers to provide parts. So they write a contract with a specification, and the parts arrive at the company from the supplier, and they are expected to meet the specification before they get paid. So if there's a mismatch between the supply chain equipment and operator measurements and the incoming inspection at the company, operator and equipment, a part that would look correct within specification at the supplier might be out of specifications at the company. So GR&R is an excellent way to resolving these problems. In the industry, it is generally accepted that the error due to equipment and operator is less than 10% of the measurement. So that is the standardized way of measuring it. We're going to look at two ways of doing it. One is to use that 10% in a method called X bar R method, and then to look at the significance, whether the use of the equipment is significant, makes a significant difference in the measurement, or the use of the operators makes a significant difference in the measurement. All these things were developed, GR&R was developed prior to World War II, when the government said there'll be 2 suppliers for every piece of equipment, and forced companies to, instead of using their own parts, to use parts from their competitors. So it was set up that way, and then we still have it that way. It came back as we started doing the supply chain, as most companies rely on the supply chains for their parts today. So in this example that we did on week 3, we have a system where we take 10 parts that come out, 10 successive parts that come out of a production line, and we have 3 operators, and each operator measures the 10 parts. They all have to meet the same specs. Each operator measures the 10 parts 2 times. So there is 10 parts, 3 operators that measure each part 2 times. So that would be a total of 60 measurements. And that's what we see here in the solution for week 3. So we see operator A measuring the 10 parts, and we call the first measurement trial 1 or first trial, and the second measurement second trial. We provide an average for each operator and a range for each part, and a range for each part. So we do that also. So operator A measures 10 parts twice. So operator A makes 20 measurements. Operator B makes another 20 measurements on the same 10 parts, and operator C makes another 20 measurements on the same 10 parts. 10 parts repeated twice by each operator. We get an average range for operator A, an average range, so that is the average of the 10 ranges for operator A, for operator B, average of the 10 ranges, and for operator C. Then we have a total R average. That is the average of the 3 operator ranges. So R average is 0383. Remember that number, we're going to see that later. And the XDiff, which is the difference between the 3 operators. The 3 operators have an average of 0.82 for operator A, 0.76 for operator B, and 0.8275, same one as operator A and C. So the difference, XDiff, that's the difference between the operators, is 600. So from these, we derived equipment variation, which is essentially using D2. D2 is a conversion. It's called an R bar estimator of sigma. It converts R bar to sigma. So that is sigma of equipment variation. That's the sigma of the equipment. The EV, which is equipment variation, it's 6 sigma of the measurement. So 6 sigma is a span. Normally, we used to use 515, which compromises 99% of the range and then the normal curve. Now we use 6 sigma, which is pretty much the whole range, and it's 6 times the sigma. Then we have, so that measurement looks at equipment variation and measures it as a total of the total variation. We'll see the total variation very soon, and that is 18% of the variation, total variation, is due to the equipment. And of the tolerance, it's 1.36% of the tolerance. Remember that the tolerance span is 7.5%, or 7.5 on either side, plus or minus. The span is 15, so there's plus or minus, and there's the span that covers all of it. So the operator variation, sometimes called the appraiser variation, measures the difference due to the operator. And if you remember, we take out of the operator variation is the sigma of the equipment. So we convert XDiff in this formula here. We convert XDiff, I'm trying to point that out, to sigma by D2 star, to D2 star. It's a conversion of XDiff to sigma, and we take away the equipment variation. Again, we get the same numbers, which is the sigma, then the appraiser variation, which is the 6 sigma, then we get the percentage due to the total variation and percentage of the tolerance. A GRNR is a root mean square of the 2 values. And again, we get the 6 sigma of sigma GRNR, we get the percentage of total variation and percentage of the tolerance. Now, the part-to-part variation is another estimator of the sigma of the parts. So again, we have 10 parts. Each part is measured by 3 operators, and every operator measures the part twice on the same machine. So every part average that we see at the end here, every part average measures the average of this for the same part, the average of 6 measurements. 3 operators, each one measures the part twice. Then what we do is we take the range of part averages and convert that to sigma for sigma of the parts. So when we look at the sigma of part-to-part variation, we take the maximum minus the minimum right here, 101 minus 45. So the maximum is 101, which is part number, I'm not sure what that is, maybe part number 6. And 045 is the part above it, part NQ26 and NQ27. So these are the 2 parts that we're measuring, and these parts will give us the range, and the range will give us the sigma of the part-to-part variation. So there's the range. And you convert that to sigma, again, taking a range difference. So it's a difference in X bar, it's an X diff, and you take D2 star, which is an R bar estimate of the sigma. And we get 0.1757. And again, it's a percentage of total variation. So most of the total variation is due to the parts. And you divide that by percentage of the tolerance, and that gives us the percent of the GR&R, percent of the tolerance. So the total variation, again, is the GR&R and the part variation, and we get that number, and we're there to go. So essentially what we got, the total variation as percentage of the tolerance. So the total variation is 108. The tolerance is 15, which is the span. So that's 726. And then that works out everywhere. So now if we do it using the ANOVA method, the additional information we get is significance, which is based on probability. It is not based on percentages. So that gives us an idea whether the difference is due to the parts. The difference is due to the parts is measured as a probability. If the difference is lower than 0.5, 0.5 is kind of a magical number. If it's higher than 0.5, part-to-part differences as measured by the equipment. Remember, parts are measured by equipment. So parts indicates equipment error, indicates as the measurement of the parts. If it's low, that means parts coming out of the production line are significantly different. That's not good. In terms of the operators, that means we have 3 operators. By the way, we have degrees of freedom here for the parts. There's 10 parts, and we have 9 degrees of freedom right here. And the probability due to the operators, so that is the significance due to the operators. That means the differences between the operators is significant. So therefore, in terms of the parts, we need to look at the machinery that makes the parts. In terms of the operators, we need to look at the training of the operators that operators would measure things. I mean, if operators are reading a dial, that's fine. They can record the dial or can read the dial differently. If it's an LED display, they can write it down wrong. Or if they're using measurement instruments such as a micrometer or vernier, they don't know how to measure it or they don't know how to read it. So there's training involved. So either for the parts that the production line equipment maybe needs calibration, maybe needs lubrication, maybe some of the tools, if it's a machine part, if it's screw machine parts or milling machines, the tools, the drills, the cutting tools need to be sharpened, and they need to be scheduled to sharpen them. The equipment needs to be calibrated. The operators need to be trained. So that is what's telling you with the probability. It says the parts to part, as they come out of the production line, are significantly different. The operators from one operator to the other are significantly different. There's another indicator or source of variation that's not shown here. I did not ask you to do it because I don't want you to do a lot of math, since Minitab will do it for us. It is the interaction of the operators to the parts, which means operator A working on a different machine makes a difference. The combination of operators and machines makes a difference. That's also very bad. If certain operators with certain machines gives you good results, and other operators with other machines give you bad results. So the interaction, if it does show up as significant, is another problem in terms of calibrating the instrument machines as well. So now we have the total of 59 measurements. That's 60 minus 1 degrees of freedom. 9 for the 10 operators, 10 minus 1. 2 for the operators. Repeatable is 48. These are extra measurements. In reality, all we would need is 10 parts measured by 3 operators, right? We'd need 30. But repeatability means these are all extra measurements to try to give us a sense of the variability of the system. So that's the way we do GR&R. So X bar R method is percentage, and we want the measurement to be less than 10% of the specs. So if we look at the variation, the total variation, we meet that. The variation is 7% of the specs. It's less than 10% of the specs. But there are problems with our operators. Our operators are not, although they are within the error, the difference between operator to operator is significant. So we want to make sure that there's a training involved. So we look at that percent variation of the tolerance. Of course, that's a very wide tolerance, considering the measurement of the system. So anyhow, that just gives you an idea of the way these numbers spread. Also tonight, also this afternoon, we're going to give you an example how Minitab measures control charts. So there are two kinds of control charts. One is a regular X bar R control chart, and that is, it's a description or a chart of sample averages. So you take a sample, you design the control chart limits, and the limits sit at plus or minus 3 sigma. Then you use that history to preserve the way production operates on day one, or the day you decided to control chart the system, the production system. Then every day you would take a sample and then plot the sample average. That's the X bar. So this point is an average of 3 measurements. That's the way you set it up. And you run it every day. Now, the control charts are given or calculated from day one. Right now in the example, we're calculating it as we go along. So every time we have a red mark, it's either lower than the lower control limits and higher than the upper control limits. Just to tell you that control chart A is a chart of sample averages, which is always normal no matter what the population is. And B, control charts, if you're out of control, it does not mean you're out of spec. It just means today, the sample average of today does not meet the historical standard. So you could be out of control, but not out of spec. Now, part of Six Sigma is to have wide enough specs so that if you're out of control, it's not a disaster. You can still ship the parts. You do not have to rework them. If you're out of specs, you have to rework them because your customer will not pay for those parts. Okay, so this is the X bar R chart and the 3 sigma limits, and then the range. So that's the range, and then the upper and lower control limits represents the 3 sigma limits, and you get those from a table, as we did this in week 5. Now, if you are working in a factory which doesn't make a lot of parts, such as aerospace or rockets, where you don't make thousands of parts a day, maybe you make a few a day, we have control charts for individuals, which we call moving grain chart. So now you have a sample of one, and when you do the X bar chart, it's a single measurement. So you can see here, there's 10 measurements. In this case, there's 10 parts, so there's 10 measurements, and the X bar is the average of the 10 measurements. Now, then what we do is we take 2 successive measurements, and that's the moving range system, 2 successive measurements, and convert that to sigma, which would be sigma of the population using R bar D2 estimator, but then convert them back to individual, which is from sigma of the population to sigma of the sample, and that is dividing by the square root of n, and the square root of n would be here too. And then you can see we can only chart from the second observation, because the first observation is only 1 and it doesn't have any variability. From the second variation, and we chart the R bar. Then next we're going to do the P chart, and there's two kinds of P charts. One where the P chart is kind of a percentage, and one where the sample taken is variable, so the sample changes. When the sample is variable, the control limits are variable, and I showed you how to calculate that. Or you take a constant sample, and when you take a constant sample, you only enter the proportion each day. So you only enter the percentage each day, how many failed in that sample. So it's a little bit less math than a variable sample. Now, a variable sample could be is because your production levels changes every day. You're not constant every day. Now, remember, these are all sampling. You're not measuring every unit. So the control chart limits, the X bar R, is sample averages. Each point is a sample average. The moving range, each point is individual. The P chart, each point is the rejects in a sample. Okay, so the sample could be constant or could be variable. Obviously, you want a sample large enough so that you can detect defects. If the sample is too small and your quality is good and you have all zeros, that's not a control chart. It's not telling you what's going on. So as you approach Six Sigma, P charts don't work because your sample size will be so small, might as well do 100% inspection. Or you do automation, so you don't have to do any inspection. The automation just gives you the number if it's pass or fail. Two other charts is NP chart, where the NP chart is very similar to a P chart with constant sample. So you only have one control limit instead of variable control limits. And then C charts is you don't need a sample size. It is defects in time or space or within geometry. So let's say if you're making car doors, it's blemishes on car doors. So there's very accurate specs or very precise specs on what a blemish is defined as, like what's the size of the blemish, how big it is. It's like when you rent a car, they have a measurement and says if you have a gash, if you hit something or somebody puts a gash in your car, they say 3 inches or 6 inches or whatever. Actually, I rented a car in Europe, and the guy came out with a magnifying glass looking for scratches. That was really scary. So a little bit different in Europe than it is here. So in a C chart, you're either bounded by physical or geometry, such as a car door, blemishes on a car door, or you're bounded by time, defects in a shift, defects in 2 hours. So it's just different ways of doing it, so you don't have to have a sample size. You just time or space is the C chart. So you can use C charts when you achieve Six Sigma. Okay, I guess we spend some time now. So let me look at how to use Minitab. So I'm going to switch it to Minitab, and what you're going to have to do in Minitab, make sure you have these two PDF files of the solutions to check on your work. So let me go back to the beginning. So when we look at it, we're ready. So this is the calculations that we did, and then we'll go with the GRR, and this is the calculations we did, and we'll see how Minitab will do the same thing. So in order to get to Minitab, you're going to have to go to UMass Lowell, and it resides on VLabs. So you type in VLabs in the search. It comes up, says VLabs. You click on VLabs. Then you say access VLabs online. I don't download the client. I just use it online. So essentially, it comes up as the VLabs screen. You accept that, and you enter your credentials. Okay, there's my credentials. It's asking me for the password, and we get the top page. Now comes out of a central computer at UMass Lowell, so obviously it's going to be a little bit slow. So we go to General Engineering 2. There we are. Takes a minute to load, and then it will give me, hopefully, the contents of General Engineering 2. There we are. So we go into the Windows, we scroll down until we get Minitab. So Minitab is, the way I recognize it over here, I don't know if you can see it, it's too small. It's a symbol of like a bar graph. So we hit Minitab and we get the top screen of Minitab. So just say we don't want to do this at this time. I don't know what that is. And we say done. So we're ready for Minitab. Now, I've prepared an Excel sheet, and that Excel sheet contains all the information you need to do this. So we go to Minitab. I'm sorry, we go to, let me get this, we go to the home computer at UMass Lowell, and we go look at this PC. So essentially, I am in my OneDrive right here where I have the Excel file. That Excel file is available to you on week 8. So we click on that. And what I'm going to do is, I just did it. So, and I called it 3.23. I will load that in your system because I just modified it this morning. So I asked for that. And what that has is all the raw data that we're going to do our analysis. We do not want to install Excel. It's already installed. So it's going to come up, load up Excel, and has all the data we need to do our work. So it has, right now it highlights the Excel, and it goes up to 60, highlights the 60 measurements for GR&R, and I'm going to copy them. Well, let's just copy the results column for now. So we'll copy the results column, comma. And you can see the way it's organized. It's organized by run numbers of the first 10 parts, and the first 10 parts sees, this is the run order from 1 to 60. Run order from 1 to 60. The parts go this way: 3 1s, 3 2s, 3 3s, 3 4s, 3 5, all the way to 10. So you have operator 1 2 3 for part 1, 1 2 3 for part 2, 1 2 3 for part 3, etc., till we get to 30. When we get to 30, when we get to 31, it starts repeating itself. So essentially, the second 30 is at the bottom of the Excel of the first 30. So we copied column D, which we're calling results. We go to Minitab, and we go and try to do the GR&R. So take it slowly here. We press on Stat. We press on Quality Tools. We move over and do GR&R. We move over and says Create GR&R Study Worksheet. It says Plan a gauge R&R and create a custom worksheet for data collection. Boom. Okay, then it asks me, it comes up with the screen. I can't make it much bigger, so I hope you can just follow it as you go along. It says number of parts is 10. Number of operators is 3. We'll call the operators ABC. It's easier because that's how we call them in the homework. ABC. Okay. So we have 10 parts, 2 replicates, and 3 operators. ABC. Let's look at the option. Okay. Oh, sorry. I made a mistake here. It's a C, not a B. Okay. Options. Very important, do not randomize, because I gave you the data as sequential. So do not randomize. So okay, okay. So what happens is it says it's a GR&R study. There's 10 parts, 3 operators, 2 replicates, total part 16. This is what we already did. Now, what you do is you go here to View on the top. You select data only, and this is the data they did. So you can see the run order up to 60. The parts, every part is measured by 3 operators. So all I have to do is go here. Now notice I go here right below C4 because you can preserve the title, and I hit it. So these are the results, which is the title, and we go and we see that we indeed pasted 60 measurements. So now we can do the work. We go back to stats. So now it made the table for us. We go and measure the 60 parts, and then we enter the 60 parts measurements in that column. Of course, you don't want to confuse them. Want to make sure it's the right part with the right operator and the right measurement and all that. So don't make any mistakes on that. So we go back to quality tools. We go back to gauge study. We go across to nested. I'm sorry, crossed. So why is it crossed? Oops, sorry. Let me go back and read what it says here for cross. Stat, quality tools, GRR study crossed. It says, access the variation in your measurement system when every operator measures every part in the study. Well, that's what we want. Now, it will show the part numbers, the operator numbers, and the measurements. So the way it works, you can see the cursor right here stuck at part numbers. So you hit C2. You either can double click it or you hit select. So that puts in the parts where it says part numbers. Operators is we want the operators. So the cursor moved directly to operators. We go to operators. We can double click operators and it comes right through. And then measurement data is where I put in the results. So there's the results. There's the measurement data. Let's start with X bar R because that's the way we did the homework instead of ANOVA. Let's look at the gauge information. There's gauge name, date of study, reported by. So let's put your name there. Make sure that you did it. If you're not going to put your name there, I'll take some points. Sorry. Okay. And that's it. Options. You can put in the specs. The way I put this, the spec is I can put it as minus 7.5 lower spec, and then 7.5 as the upper spec. That will give you the percentages of your study. Hopefully that will work. I haven't tried it before. And then we're ready to go. There we go. We're ready to go. And it's doing its thing. Then it gives you the output. So it gives you gauge R&R study results. I put in my name, so I'd like you to put in your name. And, you can put in the other numbers if you want, like the date of study and things like that. So let's not worry about the variance of components for now. Let me explain to you the gauge variation. See if I can make this any bigger. I'm not sure I can. No, let's look at view of data only, of output only. View output only, so you can only see the output. Let's make it bigger, so hopefully you can see it bigger. Yeah, it's a little bit bigger. Okay, so this is what we've done in the gauge evaluation. So if you look at the repeatability, it's 033972. Reproducibility, that's the operator variation, 030455. 033, 0304. And then there's the Six Sigma data, and there's the percentages in terms of the tolerance was 182 and 136. I'm sorry, 136 and 122, and then percentage of the total variation. So let's look back at our analysis, and there is our Sigma EV. It's 033, which is similar to what we've seen, and it's 136 for the total tolerance, 1872 for the total variation. 136, and there is the reproducibility, 0355, 16% of the variation, of the total variation, and 122 of the tolerance. We go back to our gauge evaluation, and you can see the same numbers we did. 136, 122. So it matches exactly what we did. No pain. Getting the calculations here. The process tolerance is 15. And there is all the numbers that we developed. Now, if you want, in your report, you're going to give me those values. So the way you do this is you go to worksheet 1, you right press worksheet 1 on your mouse, and it says send to Microsoft Word. So when you do that, it will send it to Microsoft Word, and then Microsoft Word appears at the bottom. So here's Microsoft Word, and you can see they copied automatically to a Microsoft Word sheet, and there's all the data that we just did. So this is what you will use to send me the report. Please do it in PDF. It's a little bit easier for me to process, and I can look at it very, very quickly. So all the numbers we did in the homework 3 appear now in Minitab. Okay, so just to verify, the total variation is 108. It's a 100%, and it's 726. Total variation is 108 and 726 as percentage of the specification. So it matches. It matches our hand calculation. 108, it's 100% because everything here is from total variation. It's 726. 726 right there. Okay, so it matches. Now, the top part here of variance component, where did they get that from? Well, variance is double the sigma. So if you take every number here, let's say like if I take total variation, and I will put in the number in my calculator, 0181458, and square it, I get this number up here, 0322971. Okay, so it's essentially variation component. It's just the square of the standard deviation, and then it gives you a percentage. I don't know why they did that, just to kind of give you more data. Then there's these graphs, which I want to discuss with you very briefly for the GR&R method. So what they do is they give you 3 colors, contribution of each component of variation. Okay, so that's the percentages that we did. Percentages of total variation, okay, which is the thing we calculated, and then percentage of tolerance. Obviously, the percentage of tolerance is going to be small because the tolerance is wide. So the percentage of tolerance is yellow, which is very small, and these are the percentages. These are just a tabulation of the same percentages. Then what they're going to do is they're going to give us an X bar R chart of the data by operator. So what you will see is you'll see operators A, B, and C, and there is 10 parts for each operator. Remember, each operator measures each part twice, so that's the average of the 2 parts. So if you remember the R bar 0383 R chart by operator, that's the grand R bar that we have in our homework. 0383 is the R bar. 0383 is R bar, and you can see that is, I don't know if you can see it, it's a little small. That's the one right here. R average 0383. That's the R bar. Now, so X bar chart by operator is the operator average, and the operator average is 08.8075, which is the X bar average, the average for all those numbers. And then these are the control chart. That is not the control chart that we're going to do that we did in homework 5, because remember, that is 3 operators, and each point is the average of 2 measurements. So it's not exactly the same upper and lower control limits. This is results by parts. As I said, this refers to parts average. So this chart is really a chart of the parts average, and if we look at it on the top, that's the part average. That's a chart of the part average. And remember, every average here is an average of 6 measurements. Okay, so you can see the parts average, and you can see the average of the 6 measurements. And this is the lowest, and this is the highest, as we did before. So it's number 5 and 6. Now, this is very interesting. This is a box plot of the 3 operators. Now, the box plot, the way it measures is it gives you the maximum and the minimum for each operator, and then it gives you a box, and the box is the 25th percentile, the 50th percentile, and 75th percentile. So what it does, it tries to show you a measure of the normality of the operator. So if we look at the 3 operators, operator B is the best operator because its center line is right in the center of the min and the max, and the 25 and 75 percentiles are fairly centralized in between the min and the max. So it looks, we can draw a normal curve across, and it looks pretty good. Operator A is biased to the top, and operator B is biased, really biased to the top. So operator C is a very bad operator. So we need to work on operator C. You can see the average is 081.08. So the average is 0.08 is the main average, and operator 2 matches that, and the other 2 operators are higher. And then this is the interaction. So the way this you read this is there's 3 colors for operators A and B and C, operators versus parts. So these are 3 operators. This is versus the parts. So some parts, the operators did not do that well. I mean, I played with these numbers. So I made part 10 measured differently. So it shows. It says for some reason, part 10 was measured differently by 3 operators, while part 6 was very close. So this is a measure of which operators, which parts. So you can go back if you have a problem, look at the parts. Is there something in the part that confused the operator? So that is X bar R method. Again, all you have to do is go this way, send to Microsoft Word, and sends it to a document, and then you have that document to do it. If we want to do stat, quality tools, GR&R study, and we go back to crossed, and this time we're going to do the ANOVA. Okay, same thing. We don't have to really redo everything else. It remembers everything we did. So we're going to just go ahead, and it does it. So if you look at the ANOVA, this time we have parts times operators. So it looks very much like the ANOVA. So if you look at the total, parts is 205, operators 04, and the total is 2.24. Let's look at the ANOVA we did as a homework. Parts are 205, operators is 048, and total 2.24. So it matches. So it did it automatically. It gives us, again, the variance components that we saw before. It gives us the gauge evaluation we saw before, and then the ANOVA. And it looks very much the same. The only additional information we have is interesting. I was just going to say, it did mention my name, so I'd say, you really don't have to do X bar R chart because this does both. It does the ANOVA and X bar R chart at the same time. These are the same numbers, but when we turn it in, do turn it in to me because I want to see both X bar and ANOVA method with your name. And this is the, it says operators 033. And the reason for that is the operator, parts times operator, is the interaction. It's 9 times 2, so you get the 18. Then the repeatability represents the second 30. So the first 30 is divided into parts. 10 parts minus 1 is degrees of freedom is 9. 3 operators minus 1 is 2. Parts times operator is 18. It's 9 times 2 is 18. The second repeat is 30 because remember the second 30 is on the bottom of the first 30. And that gives you a more of a breakdown. And again, if you take my DOE course, we'll look at how we can pool and how we can get it to look like take away the parts versus operators as well. So this is how to do GR&R and how to interpret it. And this is telling us some bad news, that the differences in parts coming out of the production line is significant. Difference due to the operators is significant. Difference due to the operators versus different parts is significant. Although our measurement, because our spec is so wide, our measurement is okay. It's less than 10% of the measurement of the gauge. R&R is okay. It's 7%, right? What was it? I know this looks a little bit different. I guess we're going to go to the X bar R method, and the percentages is 7%. That's terrible. That's below 10%. But if we go to the ANOVA method, it's telling us some bad news. It's telling us, hey, the parts come out of the line significantly different. The operators are significantly different. And when the operators measure the parts, different machines, is significantly different. So we got some problems here. We need to work on the production line. What you'd like is the probabilities to be all above 0.05. So that completes the GR&R issue. Okay. Excuse me. So now we're ready to do the control charts. So what I'm going to do with the control charts, I'm going to make it very easy for you. I'm just going to copy all these columns. Okay. Whoops, sorry, I didn't copy it correctly. First of all, we got to go to the top and copy all the columns. Okay, we copied all the columns. We go to Minitab, and now if we go look at view and we see data and output, we have control worksheet number 1. So what I suggest, either you start again all over, or the easiest way is to go and say File, New Worksheet. So now we have worksheet 2, and worksheet 2 is going to contain all the control chart all the control chart data. So let me go to View, Data Only. This is my data. And I'm going to go here and just copy. Paste. So first column is X bar, and there should be 60 measurements of X bar. So these measurements are arranged in 20 samples, each sample of 3. Then we have the moving range, which is the first 10 of those. I just copied them over. Then the P chart. These are the P chart defects and different sample sizes, or same sample size. And then NP charts, which is different rejects per sample of 20, and then C chart, which is just the charts themselves. So I can just use them without having to go back and forth to show you. Okay, so we go to Stat, Control Charts, Control Charts, X bar R. Stat, Control Chart, X bar R. Okay? So there's the control charts. It's a little bit tricky because we want to get these columns here. So what you do is you hit this subgroup size. It shows you all the columns. So the first thing we want to do is we say all observation of the charts are in one column. So first thing we want to do is we want to do X bar. So we select X. Oops, sorry, we were in the wrong place. We go put the cursor here, and we want X bar. I'll double click on it. It shows up. That's what we're going to do. The subgroup size is 3 because this data is organized 60 data points of 20 samples. Each sample is 3. We'll look at the scale. We'll just let them do the scale by themselves. We'll look at the labels. And again, we want to make sure that this is Sammy, Shina. I want to make sure you do that so I know you did it. Multiple graphs, sure, we use the same one, that's fine. Data options, specify which rows to, we're not using any tricks. We just, this is if you divide up your data into different tables. And the X bar what is it called? X bar R options. This is if you have your own mean and your own standard deviation that you want to enter. If you want to do is, if you do not want to use the mean and standard deviation that we get from the data points. Excuse me. And then we go, yes. Okay, so these are the same charts we saw before. The average is 8075. Upper control limit is 0.9 and 0.7. Let's look at the data only. View output only. So there's the control chart. My name is all right on it. There's the X bar R chart and the R bar chart, and it gives you the test results of the data. These are exactly the same data that we did, and this is the chart that we have in homework 3. So I'm going to close the X bar R chart, R chart, and there is the data that we did. Looks exactly like the same data and the limits that we did in the homework. Okay. Now we're going to go back to do, and again, you go here and you send it to Microsoft Word, and then you have it in your report. You right click on the worksheet and you have your report. Next thing we're going to do is stat, control charts, variable charts for individuals. We want to do it for individuals. So I like to use IMR, monitor the mean and the variation. So if we do that, it says, what variable are you measuring? I'm measuring the moving chart. Now there is no size number, so it's no problem. And then the scale is chosen by the system. The labels, we put in Sammy Shina eye chart. And then multiple graphs, they're going to have the same Y. Data options, straightforward. And then options of IR, we don't use outside means and standard deviation. We're going to use the mean standard deviation from the data. And we go, OK. I plotted the eye chart. So very straightforward. It looks exactly the same as we did it in the homework, which was, you can do I or you can do moving range. You're going to get the same exact data with an average of 81 and a moving range of 0.111. Let's go back to Minitab. So if we want to do it, the moving range, we go stat, control charts, individuals. We can instead of doing IMR, we can do moving range. I haven't really done this. We'll just see what it looks like. So we do the moving range, select, scale, same, labels. We'll just say Sammy Shina MR chart. I make the typing mistake. And we're ready to go. All the rest are the same. So we got a little bit different moving chart. And I think in this particular case, the moving chart is, you can say it is really the range. That's really the range chart, because you can see the moving range average is pretty much the same. Moving range 0.1111, and there's the moving range 0.111. It looks a little bit different because the scale is a little bit different. So they're only giving you the moving range R bar chart. They're not giving you the X bar chart. Okay, that's the difference. So the upper spec limit is 0.3 and the lower spec limit is 0. 0.3, 0.0. It's only what they do if you do the moving range itself instead of eye chart. You're going to only get the bottom graph. So I'd like you to use the individual, not the MR chart. And notice it starts from number 2. Okay. Now let's do the P chart. Let's look at the data. View, data only. So for the P chart, we have the P chart and the sample size. Okay. So we'll go to the P chart, stat, control charts, attribute charts, P charts. So now we're in P charts. So let's make sure we got the right titles. So we got P chart. So let's look at P chart. and we select it, and the subgroup sizes is in the column P sample size. P sample size. And we bring it here, P sample size, scale, same, labels, Sammy, Shina, P chart. I guess charts would be C capitalized. I think I did that right. Yep. Okay. Multiple graphs, same. Data options, same. And P chart options, we don't want to have our own proportion. We're going to use the one from the data, and we run it. There's our P chart. Let's look at the view of output only. And you could see it looks very much like what we did in the homework with different upper control limits because of the different sample sizes. Okay, and you can see that very easily when we did it, and we did the calculation. There it is. This is one is for constant, and this one is for variable. Now I could do the P chart for constant, but really P chart for constant becomes an NP chart. It's really the same thing. So I'll do the constant for the P chart, and then we'll do the NP chart. So let's go back to our constant. So we go stat, control chart, attribute chart, P chart. So in this case, on the sample size, we can put in sample size 1. Sorry, first we got to delete that, and then we put sample size 1. Labels, again, Sammy, Shina, P chart. Constant sample. Okay. And we run it, and there's our constant sample P chart. So it looks, again, very much like the constant sample that we saw here. P chart subgroup of 20. And that's what we have. It's exactly the same chart. Now, what it does then, it uses the formula for the P chart with each constant sample being the same. Just as a reminder, this is what the data looks like. View, data only. So there's 20 in each one as opposed to the constant sample. If we want to do an NP chart, again, we said sample size is 20. There's a reject in a sample of 20. And we can plot that very, very easily. Stat, control charts, attribute charts, NP chart. So now we're doing the NP chart. We selected the NP chart. So we said the NP is the NP reject data. And we do it. NP reject data. Subgroup size is 20. Labels, Sammy, Shina, NP chart. Hit it, and we get the NP chart. Let me turn that down a little bit so we can see there's the NP chart. And it looks the average is 4, and the upper average is 9. Upper control limit is 937, and that's exactly what we got with the NP chart. 4, 937, and 0. Very, very similar. Now, the last thing we're going to do is the C chart, which is just a column. So there's really no problem there. If we're going to look at this fully, view output only, there's the NP chart. If we want to bring it over to the Microsoft Word, we right click on worksheet, we send to Microsoft Word, we go to Microsoft Word, and there it is in Microsoft Word. Okay. So it copies, and this will be part of your report that you're going to turn into a PDF file and send it to me. If you can compress the pages, it would be good. It'd be easy for my thumb and my index finger that rolls the scroller. But do the best you can in this case. Now, the last one is going to be the C chart. So let's look at the data. And the C chart is in this column C12. So we are going to say stat, control charts, attribute charts, C charts. There's our C chart. We go to column C12. We double click it. C reject data. That's it. Scale is to index. Let them decide on the scale. Labels. Sammy, Shina, C chart. Okay. Multiple graphs. We accept. Data options. We accept what's available. Each chart option. We use the mean from the data and do not provide an outside mean. And we're ready to go. And there you go. Let's view it as output only. And there's our C chart. Average is 2, upper control limit 62.4, and lower control limit is 0. We go back to our C chart. Looks exactly the same. C is 2, upper control limit 6, and lower control is 0. And we go to worksheet 2. We right click. It says send to Microsoft Word. You do that. You go back to Microsoft Word, and there's our C chart in Microsoft Word. So this kind of concludes our Minitab session, and we will see you in the live chat, and we'll ask any questions or answer any questions you might ask or have, or any concerns you have. This concludes our demonstrations. Thank you for watching, and we'll see you in the live chat.